Can I start filming?
Yes. Okay. So the big idea is that we're now coming to the end of stuff that has. We're coming to the end of stuff that seems like first year calculus. We're now sort of moving into a new space, a new way of doing math. So I want to say what Green's theorem is about, and then we'll start setting up the tools to do it. In one variable, we have the incredibly beautiful fundamental theorem of calculus. Right, so we've got our function. We have some values a and b. And then we slice up the area under this function. A bunch of thin strips, and when we add up those strips, we get the total area. So fundamental theorem says says the following thing. So one way to think about this is that an integral over a region is equal to a function at the boundary. Okay, so we're integrating over this region. Right? And what the fundamental theorem is telling us is that the only values that matter, the important values, are those endpoints. So an integral over a region AB equal to somehow a function at the boundaries. Now, for an interval, it's only got kind of two boundary points, A and B. Okay. Right, so what we want to do is we want to lift this to 2 dimensions. We want to think about how this theorem could work 1 dimension up. So somehow what we're going to say is something like, right, we're going to say a double integral over a region something something involving the boundary of the region. Okay, so to lift the single variable theorem up to 2 variables, we need to get clear about what the boundary of something is. Right, so to get a mathematical definition of the boundary of a region. Okay, so looking at this example of intervals, these guys have, the numbers A and B have special properties with respect to this interval. We want to get a sense in which these are the boundaries of this region, right? if you approach one, as soon as you step past B, you have left the region. Or as soon as you step past A, you have left the region. So we want to make a definition out of this. Okay, we want to make a definition that would work in any number of variables. So we want to define that these points are special because every move we take to the right of this leaves the region. Every move we take to the left of this leaves the region. So the boundary of a set is going to be all of those points just a little bit of notation from Math 102. This is the set complement. So that's the set of things that are not in S. Right, so every disk centered at B meets our set S and the stuff not in S.
Can you, like, what do you mean by centered at X?
Right, yeah. So I take this point B, I draw a disk around that point.
Oh, okay.
Yeah, so I really mean the center of the disk.
Okay.
Okay, so that's our sort of notion of a boundary.
Just one more thing.
Yeah, sure.
So when you say about like the center, so any point near to the B, like a bigger size disk can also be called, no?
Right, yeah, so the important question here is that this works for every size of disk. Right, if I draw a tiny disk,
Okay.
it still meets S and not S. If I draw a really tiny disk, it still meets not S and S.
Yeah.
Okay, so
The
very, very small.
The boundary.
Okay. Okay, so we want to find the boundary now of a region in the
Circle.
plane. Yes, circle.
You like circles.
So this is the kind of thing that maybe little kids could do. Say, there's the boundary. We found it. It's this stuff, right? It's every guy on the circle. If I draw a disk around it, it meets my region and it meets the complement. Any tiny little disk will meet both the set and its complement. So oftentimes when we're doing these boundary calculations, if we've got a less than or equal to sign, we wind up with an equal sign. Okay? A nice, helpful way to remember that. There's a piece of notation for the boundary. The boundary of S is the partial derivative symbol S. So we put this partial derivative symbol and then the set S. So this is how this is often written down. So we could say and if we want the boundary of this set, we get just a pair of points. The boundary of the closed interval is just the endpoints of the interval. Yep. Oh, is there a question? It's unclear. It's dicey. Ponder it a moment. Take a moment.
No, like this interval, this is the interval, 0 to 1. This is the interval. But there's one. Open interval is boundary.
Have you got it? You okay, the question's good now? Okay, cool. Sweet. Right, so yeah, we've got this notion of a boundary. Now, there's a corresponding thing that we need, which is a definition of orientation. We've seen that orientation, if we go in one direction, we get positive. If we go the other direction, we get negative. So we need to define what an orientation is. So, like, just looking at this boundary of a circle, right? It doesn't come naturally with an orientation. We just get a circle. And it's not clear if we've got a clockwise circle or a counterclockwise circle. Right? There's this way, and then this way. Right? The circle doesn't come with that, so we need to define what we mean by an orientation. define orientations for simple closed curves. So at the end of Thursday's lecture, we defined these notions of simple closed curves. Right? Curves that have no self-intersections, that close up to form a loop. And in some sense, they all look like this. Right? They form a loop, no self-intersections. And we can choose to orient them either clockwise or counterclockwise. Okay. So if when you're tracing at the curve, it seems to be going in the same direction as a clock, right? So it seems to be going in the same direction as a clock. Call that a clockwise orientation. And this would be counterclockwise.
Choice of parametric. Parametrization. It's a choice of parametric.
Okay, so a boundary, we can have a clockwise orientation or a counterclockwise.